Hi, welcome to es201 Computer Techniques. This is week 4, and this is the lab. So there's an objective here. I just want to do one thing, and that's explain one of this week's lab assignments. This is hopefully a little more interesting lab assignment. We're finally starting to get enough tools where we can do some interesting things, and so I want to spend some time explaining the background behind this week's lab. So first of all, just again some definitions of where we're going with this. And so I'm just going to define a couple terms here, because what we're going to do this week is we're going to write an encryption scheme. And so just the strict definition of encryption, it's known as the process of converting ordinary information into unintelligible text. And so often this is talking about converting plain text into ciphertext. And when you're writing encryption schemes, or implementing encryption schemes, there's something known as the challenge. And what that means is that a spy could not guess the plain text without substantial brute force work, but the recipient can read it with very little work. And so this is done in all sorts of digital encryption, because you want to be able to send information very quickly to someone else that should be able to read it. But if someone's eavesdropping on you, they're listening in on your Wi-Fi network, you don't want them to know what you're doing. So you encrypt it first, and they wouldn't be able to read the ciphertext and be able to come back out and get the plain text. What we're going to be doing is a particular type of cipher. And we're going to be doing what's called a block cipher. And what a block cipher does is it converts n plain text bits into n ciphertext bits. So essentially, if you've got 245 bits going in, you're going to have 245 bits coming out. There are other types of ciphers, and in fact, block ciphers are a little easier to break than non-block ones, but that's beyond what we need to worry about here. So here's kind of like my little picture of it, right? I've got two people. They want to go ahead and talk to each other, and we want them to do that very efficiently. But we need to assume that there's going to be some spy down here that could be listening in on this, so they could be tapping into your Wi-Fi network. Now, clearly, you want to be able to go back and forth very quickly between here and understand each other. Even if this person is listening in, you don't want them to know. So what you're going to be doing is you're going to be taking plain text, converting it into ciphertext, sending ciphertext over here, and this person is going to decrypt it. So what you're going to be doing in this week's lab is you're going to be writing the encryption scheme, the point of which you're going to take your plain text and turn it into ciphertext. Later on this semester, we're going to do the reverse, and I'll have you write the decryption scheme. So what we're going to do, we're going to implement a particular type of block cipher, and it's known as the Feistel cipher. So this is worth spending some time to explain. On the right-hand side, I show a picture of encryption and decryption. I'll come back to that in a minute. But first, I want to talk about some important components of the Feistel cipher. Feistel cipher takes advantage of what's called a pseudo-random function. And what a pseudo-random function does is it's a function, right? It's going to take, think of it as f of x. It's going to take some value of f of x, and it's going to convert it into something else. And so, for example, it might take the letter A, and it would convert it into something over here in the encryption, and maybe that over here is the letter O, say it's the letter G. And then it would take the letter B, and it would convert it over here, maybe it's the letter M. Right? And so it looks sort of random at which points it's taking in the plain text and converting into the ciphertext. And it's called pseudo-random. It's pseudo because computers do this, and every time you go ahead and get a B, you want it to turn it into an M at the same time. But if someone was just to be looking sort of like what points you're shooting in this blue target, it would seem like it's just kind of randomly hitting instead of methodically moving through the area. Okay, so coming back over here, now this is the encryption-decryption scheme of the Feistel cipher. And so this is what you're going to be implementing. You'll be doing just the encryption scheme at this point. And what you're going to be doing is you're going to be taking some text letters, and you're going to start off with the first two letters of your text. So maybe we are going to encrypt the word hello. You would take the letter H, that would be what's represented as this L0, and you would take the letter E over here. And then what you're doing is you're sort of like just mixing it all up so you wouldn't understand. So what's going to happen is it's going to come down and it's going to go through an actual type of mixing scheme. That's what this F is, and I'll explain what that is in a moment. It's going to mix it up, and then it's going to go ahead and do this little bitwise. This is a bitwise operation between these. It's another way to mix them up, and then you kind of swap these through, and then you do the whole thing again, and you do it again, and you do it many, many times, and by the time what comes out of here at the ciphertext, you put it in an H and an E. Maybe you're going to get an X and say a G down here, and so it would look very hard to looking at X and G to know you started at H and E. So what we're going to do is we're going to use a linear congruential generator as our mixing And so an LCG is this type of pseudo-random function. I'll explain the LCG, which stands for linear congruential generator. Just so you know, this is actually a pretty common pseudo-random function. It's used a lot in the standard libraries. glibc, which is the standard library that's actually in the compiler you're using in this class. Microsoft's Visual Basic uses this as well. So here's what the LCG does. It's this formula here. It's fairly simple. It says that this value x of n plus 1 is equal to, and here's the algebra, you take a value number a, it's a constant, you multiply it by x to the n, you add c, and then you take all that and you take the modulus with m. Remember, modulus is the remainder of this. So what happens is you put in x to the n, you're going to get x to the n out. A, C, and M are constants that are defined for your particular implementation of the LCG. And so let's kind of see what this does. And the way this works, kind of, if you want to think of it before I go through the math, it's sort of like if I was to take a wheel, like from Wheel of Fortune, and spin it. Maybe I spun it so hard that it's going to go through, it's going to click, say, 563 times. But notice how it just goes through a particular finite number of sets, and then it'll give you some value, maybe this number 30. Now 30 might have happened whether it went through, say, 67 clicks or 183 clicks or something like that, some multiple of it. That's what this LCG is doing. So let's kind of go to a little bit more strict example of it. So I'll go through the LCG. Let's go ahead and use these constants for M, A, and C. And I got some small values here, so that you know when these are implemented in computers, they're actually much, much larger values. But we'll do small ones so we can understand the math. So we're going to start off with a value, and let's say x to the n starts off at 0 for some reason, right? So we start off at 0, then we plug it into this formula. So I have a times 0, and so 4 times 0 is 0, and then I'm going to add 1 to it, so now my value is 1. So I'm going to go ahead and take the modulus with 9, so 1, and then what's the remainder if I divide it by 9? Well, that remainder is 1, all right? So now I've got an output of 1. So this is what x to the n was. Now I put it back in again, so this becomes my new x to the n. I do this again. So now I've got 1 times a, so 1 times 4 is 4. And then I'm going to add 1 to it, and that's going to give me a value of 5. And then I take 5 divided by 9 with the remainder, and at that point, I'm going to end up with 5. So now I'm going to go ahead and put 5 back in, and you keep doing this again and again. Now notice now I've got 5 times 4 is 20. Add 1, it's going to be 21. And now when I divide it by 9, that's going to go in twice and go ahead and give me a remainder. And that remainder is going to be 3. And so what you realize is it's sort of like like I say, it's sort of like a wheel you're just spinning around. Now notice when you have over here, you've got this value of 3, it's very difficult to know that you actually started off with 0. But it's pretty simple, the math that we just did to go in the forward direction. So that's a type of pseudo-random function. It's the one you'll use in this lab. It's called the LCG. Just to kind of give you some pictures of what this looks like, if you were to maybe use these constants, I got a whole different set now. I've got 17, 23, and 43 for my A, C, and M values. If I went ahead and seeded maybe with this value right over here, it's about 23. The next one would come over here, it's about 27. Then it would be this value. And this, I'm just kind of sequentially showing the values. All right, and if you look at this across, just kind of visually, sure does look kind of random at any particular point to know what the next value is going to be. The other thing, if I just sort of subtly change those values, so here I'm just going to change my C value from 23 to 29, notice that the sequence of values is much, much different, right? And so any small change in these constants over here, not only are they random, the difference between these random sets is very, very different. Okay? In cryptology, this is what's called a trapdoor function. It's a trapdoor function because actually implementing that LCG like we did in the previous example is actually pretty simple, given this value and you know those constants to go to this value and then go to that value as well, right? But it's really difficult to go in the reverse direction, so it's like going through a trapdoor. It's really easy to implement this way, but given the result, it's very difficult to come back in the reverse direction. Right, so back returning to my Feistel cipher, this F block right over here, this is the LCG, right? So this is going to be putting in an x to the n value. You're going to be in an x to the n plus 1 value. This circle with a plus sign, that is a bitwise operator. We talked about bitwise operators before. And so you're going to do a bitwise operator between the value of x to the n and then the ASCII representation of L0. Right? So let's kind of look at this. For example, if my text was T, E, X, and T, right? Those are the 4 things I'm going to put in. I'm going to first put a T in there, and I'm going to go ahead and put an E in there. A couple things you need to do in your program, and I mentioned this in the instructions. You're going to need to take that your initial character, for example, this t, you're going to need to static cast that into an integer, because what you're going to be doing, for example, when you're going through the LCG and the bitwise operators, is you're going to be operating on integer values. It's pretty straightforward to do that. You're just going to go ahead and define a variable, maybe call it left, which is a type integer, and you're going to static cast, and you're going to take a value of your string. Okay? You're going to use the LCG as that trapdoor function. Right? And this value k0, this is the thing, the user will input a key value, right? And k0 is the number of iterations you go through that LCG. Remember, every time it spun through, I think I did 3 spins in the previous example. K0 is the number of spins you do. And then what you're going to do with each level, each round of Feistel, each one of these is called a Feistel round. You're going to do 3 of them. Each key value will increment at 1. So if the user said start off with a key of 23, the next one would be 24, and the next one right down there would be 25. Okay? When it's all done, you're going to have what's coming out at the very bottom. You're going to have your ciphertext. They're going to be integer values, because you've been doing integer values. But what you're going to want to do is you want to output those as hexadecimal. I've got that in the template. You don't need to do it. And the reason is because it doesn't necessarily have a character representation at that point. It actually might not be a printable character. If you think back to the ASCII table, remember there were a lot of unprintable characters on there. And so we're going to output it as a hexadecimal. This is in your template. You don't need to do it, but you'll be able to see where that's done. All right, so I'm just going to go through an example here. Just take 2 letters so you kind of see what's going on in more detail. So now let's say I start off with the letters S and H. So maybe my first word was shout, right? So S over here is going to be my L value, and H is going to be my R value. Okay? Now S and H, if I was to go to the ASCII table, right? S is the same as the integer value of 115. So if I static cast this to an int, it's going to be 115. And I also just show the bit representation of it here as well. So that's S, and then I see over on the right-hand side is H. Now, H is going to go through the LCG value, so I'm going to essentially take 104. 104 is going to be my x to the n value, and then depending on what the user entered as a k0 value, that may how many times I process this through. So let's say I did that, and what comes out of the LCG now is the number 89, okay? And this is the bit representation of 89. Now I'm going to take this number here and do a bitwise operation with this one here. Remember, this is the exclusive OR. Okay, and so if I do an exclusive OR, I'm comparing bit by bit. So like for the left-hand side, 0 and 0 is going to give me a 0. The next one, 1 and 1, is also going to give me a 0 because they're not exclusive. The third place, though, is going to give me a 1. And so if I actually go through the whole thing, and you might want to pause the video and verify that, this is going to be the exclusive OR of these 2 values here. All right, and now this, let's see how these lines cross. Essentially, I just take this number right over here and send it to the left-hand side. And what I did before I processed my thing through the LCG, I made a copy of it. This is where that bifurcation is, and that's going to get sent over to the right-hand side, and it's just going to go into the next round of the Feistel, right? And so here's this, and you can go ahead and you're going to be carrying these around as integer values, and you'll just put those into the next round. All right. Just kind of a little bit of advice. This is going to be one of the more challenging programs to write. You'll do this incrementally. I've got it broken down into parts. And what you're going to be doing is you're going to do this in 3 nested loops. The innermost loops is going to be you're looping through the LCG. This will be that part right there. And then you're also going to loop over the number of Feistel rounds you do. And you're going to do 3 Feistel rounds. And then you're going to be doing that over all the characters that you do. And you'll actually be doing it in pairs of characters. So you'll do it in the first 2, and the first 2, and the first 2. So this will be a good implementation of 3 nested loops. Okay? As I say, this will be a little more challenging, hopefully a little more fun. Plan this out when you write this program. It's actually not that long, and so don't make this overly complicated. You can do this in about 10 or 12 lines of code added to the template that I give you to go ahead and implement this. So please take some time to think through what you're doing before you write too many lines and make it too complicated. So, okay, well, good luck. I will see you later.